last video, we were looking at how you can store numbers in an attribute table in GIS. We said that there are two things that you have to consider when choosing the kind of data type to declare to store your numbers, whether or not you need to be able to store fractions, as well as how large or small the numbers that you need to store are. We said that this is important and that the values the numbers can take on are not something arbitrary. Let's take a look at why making this decision is important. This is important because it has to do with how much disk space that your computer reserves to store the value entered into the cell in the field. Whenever you declare a data type, the computer establishes what are called markers to reserve a certain amount of storage space for each cell in the field. In the case of the short integer, the computer reserves 2 bytes of storage space for each cell in the field. Again, this is the amount of space that's reserved for each cell in the field, not the total for each field. What's the largest number a computer can store given 2 bytes? Well, it's 65,535. We'll look at that more in a moment. When a long integer is declared, the computer reserves 4 bytes for each cell in the field. You're doubling the amount of disk space that's being reserved if you choose to declare a long integer data type rather than a short integer data type for the field. When you declare a single precision floating point data type, the computer reserves 4 bytes per cell, and when you declare a double precision floating point data type, the computer reserves 8 bytes per cell. So now let's address why those numbers may not be as arbitrary as you think. To do this, we have to understand how a computer stores data. You've probably heard of the terms bits and bytes. A bit is the smallest unit of data that a computer can store, and it can take on one of only 2 values. Traditionally, we call these 1 or 0, on or off. So if I give you 1 bit of storage space, you could store the number 0 or the number 1. This is the smallest unit of computer storage. You can think of bits as the atoms of the computer world from which larger data structures are built. When you put bits into a sequence, you can store larger numbers by using the binary system. Chaining bits together like this is exactly how larger numbers are stored in a computer. Our ordinary system of counting is based on the decimal system, base 10, but the binary system is base 2. If, for instance, I gave you 2 bits of storage space, the largest number you could store is 3. I'll demonstrate. You've got 2 bits, each one can either be 1 or 0. So 0, 0 would store the number 0, 0, 1 would be 1, 1, 0 would be 2, and then 1, 1 would be 3. This is because instead of thinking in terms of the ones place and the tens place, as we're generally accustomed to, you have to think of the ones place and the twos place. In the first example, we have 0 twos and 0 ones, or 0. Here, we have 0 twos and 1 1, so that's 1. Next, we have 1 2 and 0 ones, or 2. Finally, we have 1 2 and 1 1, or 3. This is counting in the binary system. If you had 3 bits, then you could add a 4's place and store the numbers between 0 and 7. I'm not going to go into counting in binary into too much more detail here. There's a lot of material out there on it, but you should be able to recognize the pattern that's appearing and why this is relevant to data storage. A very common grouping of bits is a sequence of 8 of them. We call a sequence of 8 bits a byte. So think about what values you could store in 8 bits. You would have a 1's place, a 2's place, a 4's place, an 8's place, a 16's place, a 32's place, a 64's place, and a 128's place. I know that sounds strange if you're used to only counting in base 10, but the smallest number here would be 0. That would be when all of these bits are off, all take on the value of 0. The largest number that you could store here is 255 if all of the bits were on, having that value of 1. You can get to that number, 255, by adding up 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So I could store 256 possible values in a byte of information, 0 to 255. If I gave you 2 bytes of data, the numbers get even larger. I won't work through it here, but you could. Given 2 bytes of data, 16 bits, You could store values between 0 and 65,535. If you had 4 bytes, you could go up to the number 4,294,967,295. Given 8 bytes, you could store the values from 0 to, well, a very large number. So these numbers don't look particularly round to us because we're used to working in the decimal system, and these numbers are derived from a binary storage system. Now, if you're looking at these numbers and comparing them to the numbers that are allowable in the field data types, you'll notice that I just have positive numbers written here, but that the attribute table field can store both positive and negative numbers. I'm not going to get into how the computer stores negative numbers using the binary system and given a certain number of bytes, but you should at least realize that some of those bits in there are going to have to store whether or not the number is positive or negative. Since, for example, in the case of a number stored with 2 bytes, I'm going to have to use a bit in there to determine positive or negative, and that leaves me with less storage space to store the number itself. So the absolute value of the number that I can store is going to be smaller, but it will cover a positive and negative range around and including 0. So you might have noticed that, for example, the largest value that I can store in 2 bytes is 65,535 if I only cared about positive numbers. If I also needed the ability to store negative numbers, which long and short integer data types do allow me to do, I can take those 65,535 possible values and split them around the 0. That's why a short integer with 2 bytes of storage space allocated can store values between negative 32,768 and positive 32,767. If you take the absolute value of negative 32,768 and add it to 32,767, you get 65,535. So I can still hold that many different values, it's just that they're split over a range of positive and negative numbers. So let me give you an example of the amount of space that these take up in your GIS files. Let's say you have 1,000 features in a file. That means that you're going to have 1,000 rows in each new field that you add to your data file. If you know that the only values that the cells in this field will ever need to take on are whole numbers between 0 and 99, then you should declare a short integer for this field. The computer will set aside 2 bytes of space for each cell in the field for 2,000 bytes, or 2 kilobytes, right, of space that's now being taken up. If you had declared, say, a long integer, then you would have doubled the size of the file for no reason. 4 bytes would be reserved for each cell, or 4,000 bytes, or 4 kilobytes. If you would declare double precision floating point, then you would have used 8,000 bytes of space, or 8 kilobytes, and not gained any additional benefit if all you ever needed to store were the numbers 0 to 99 in any particular cell in the field. So you should think about what you need to store. If you don't need to store numbers that large in a particular field, then you don't need to reserve, say, 4 bytes of space in the cell. Save yourself the space and pick an option that consumes the least amount of your computer's resources that also stores what it is you need to store. This is going to increase the efficiency with which your data is stored and increase your performance. When you're working with a GIS dataset, it has to be moved off the hard drive and loaded into memory, the RAM, and as you probably know, you have much less RAM than you have hard drive space. First, the process of loading and unloading data into memory for processing takes time. Then the more RAM you're using just to store your dataset, the less you're going to have to perform your processing tasks. So there's no reason to do with more what can be done with less. When you're talking about using cloud-based GIS servers, you may be very well paying the hosting service provider per megabyte or per gigabyte of data that you're going to be storing on the server. Therefore, storing your data more efficiently would very directly save you money. There's no need to pay to store data as long integer if you can store the exact same thing as short integer. Likewise, if you're trying to transfer data from one place to another, from server to server, or from a server to a computer as a web page, or from a server to someone's cell phone, the smaller the file size, the better. Smaller files transfer faster than large ones, so why send a large file along a network when a smaller file could have contained the exact same information? Being very efficient in how you store data can be a big help in these circumstances. Also, many people without a background in computer or information science don't realize that you can fill up your hard drive with a whole bunch of nothing. I like to demonstrate with GIS software that I can take a shapefile that has nothing but the 50 states in it and no attribute information, and then start adding fields to the shapefile and choosing field types that reserve large amounts of space. And even though I don't put anything into the fields, the computer still sets aside the space to store the data, and the file size gets larger and larger. This is an excellent demonstration for people who are unfamiliar with this concept, and I'll try to put together a software video on that. For the most part, in an introductory GIS class, a student is most likely to encounter field types when he or she is trying to enter some value into a cell that the field is just not going to accept. That's why I'm talking about it now, because I want you to understand the problem that you're encountering on this theoretical level. But then there are also more practical reasons to be concerned with this than just the ability to enter data into a field. If you go on to further study in GIS, we'll go on to geospatial database design and hosting and serving data from the cloud, and we'll definitely look at these issues from an efficiency standpoint when we're working in that kind of an environment.